Welcome back and for our questions and answers at learnpiezo.org. In case you're wondering how to spell Learn Piezo, that's how you spell it, and you can go there for a good organization of videos. But today we're going to be going over a certain problem someone was having. Probably there's an equation for it somewhere. Somebody already derived it, but here we go. So we have a piezoelectric material applied as a sensor and what is called a unimorph. So first I'll go over these two terms. The first is unimorph, and the second is called bimorph. And I'll just give their structure briefly here in a different color you may be more interested in than this one. Okay, let's say this is a fixed wall, and we have a cantilever. And let's just call this cantilever a PZT material, or a piezoelectric. PZT stands for lead, zircon, and titanate. It doesn't stand for piezoelectric. And let's say it has a polarization direction here. And if we apply a force here, what's the voltage we'll see across this? So what's the difference in change in potential if we apply force there? Because there's tension and compression, as we know, if you have at this point and we split it up and we show the stresses occurring. So we're going to have compressive. If we're going to push it this way, there'll be sort of compressive stress, which I'll draw in this direction, and there's going to be tensile stress on the top. So tensile on the top, compressive on the bottom. If the average stress is 0, then there's going to be no force, no voltage developed. So the average stress in this material is going to be 0, although there is locally stress, which causes it to deform. So this is a cantilever piezoelectric material, which is actually going to have no voltage, which is sort of weird. What is going on here? Piezoelectric material, no voltage, weird. You apply stress. So I'll tell you why. It's because the stress, the average of it was 0 again. So how do we get out of that state? Well, we have our piezo, and I'll say the piezo material, I'll have it in a beautiful green color, because piezoelectric materials are apparently green in the sense that you can harvest energy and save the environment, but in reality the amount of energy you can actually gain from a piezo energy harvesting device is really small, microwatts, mostly, if you're lucky, milliwatts, and then you have to have a circuit to get that AC vibration, and the vibration is not always available, and there's so many different problems. I don't think it's practical at this point. But anyway, so we have this piezo in green on the bottom. We'll have polarization like that. Now here, if we apply a force, let's say these are the same. These two materials have the same properties, meaning they have the same elastic compliance and they have the same mass. Elastic compliance is more important because we're considering a static case. But in this case, we'll have, if we draw that stress and strain, again, we'll have tension on the top, compressive on the bottom. But the piezo will only be seen compressive, so the net stress the piezo sees is like the average of that. So it's sort of like right here. That's the net force. So the piezo will actually then generate voltage for you. So basically, you have to have the piezo at an off-center position from the moment of inertia in order to get net stress or in the material. The other case, if you want to do it the other way, you can apply a piezoelectric material in a bimorph configuration, in which case you can have a structure which is 100% made of piezoelectric material, but at the same time you have that case. So in this case, if we apply again a stress here, we get tension and we get compression. But based on the way we orient these polarization directions, we'll get different results. So tension here. If we have a polarization vector going up, tension, we'll do what? If you could then, now we have to imagine the positive charge, and we gotta imagine the negative charge. So basically when you pull on it, they're sort of gonna come closer together. So this side becomes negative, and this side becomes positive. So in order to get a net, if we had both these oriented positive, this would end up being negative because of compressive stress, and this will end up being positive. So these charges would cancel out actually. So then you get and the relative potential between these two is not relevant. So in order to sort of and anyways, in this case, you would sort of have this there and have that there. But a better configuration, that one makes more sense, and would get you actual net voltage, would be if you actually polarize this in the downward position. Therefore, you would get these positive charges multiplying and these negative charges appearing here. And if you hook these two up and take this out, so basically you have a wire from here coming out, and you have another wire from here. These two, you'll generate a delta V between these two electrodes if you orient them separately based on their compressive and decompressive stresses and strains, because you don't want them to cancel. So this is a unimorph here and a bimorph here. The key thing is you want some type of non-symmetry in order to develop a net stress in the piezo element. So now we'll go on to the question posed. If I have a piezoelectric, so we're going to call the red the non-active material. And if we have that big non-active material, and we have a little piezo, very skinny on there, so we can basically neglect its contribution toward the area moment of inertia. It doesn't contribute toward the stiffness. And then we introduce a force here. So this green part is the piezo. I'm just going to write it PZT. It could be whatever you want. This is the, I guess, the host material. And here's the force being applied at the edge. What is the voltage on the piezo? And so let's talk more about this structure. So the question we're answering is, what is the voltage here? The stress between these two, the piezo and the whole structure, are not the same. You know, you'd think, okay, that this point is continuous right here. Rather, it's actually not continuous there. The stress is not continuous. However, the strain is continuous, and that's the key. So strain, I'm going to write as a curly X position. If I ever use it in this, I'll write as a regular X like that. So strain is the main thing we need to consider. So let's consider, because the strain is equal, and this is a really thin piezo, we're going to assume that the strain and the thickness of this piezo is the same. However, obviously it's going to vary across here. So the strain is continuous. So in order to calculate the strain at the interface, which is, we're assuming is the strain of the piezo because the piezoelectric material is really thin. In order to calculate that, we first need to determine the stress at that interface in the host piezo. In the host material. And the stress in the host material is equal to the compliance of the host material. Alright, compliance H. And that equals the strain in the host material, which also would then equal the strain in the piezo. But that's all, we're only considering it the strain, let's say maximum, the stress maximum of that. So now we need to get into how to take this force and turn it into stress. And note that the stress is going to be varying here. So that's another interesting point. The stress is varying. So for that, I'll pause for 1 second. Okay, so here are some equations describing what's happening. The maximum stress is going to be the pressure at the end. So what's pressure? Pressure is force divided by area. Okay, so we assume that this cantilever here, it has some 3D depth going on. Okay, it's not really going to matter in the end for the voltage, but in a real problem you sort of might consider this 3D depth which is occurring. So there's force over area. The length is obviously the length of that whole structure. Z is the flexure modulus, which is defined as this. The displacement, meaning how much the cantilever tips downward, is determined by, again, the pressure, the length, 3EI, which is the elastic modulus, which then we have obviously the moment of inertia here, area moment of inertia. So now what we will continue to do is to sort of solve this until something we want. So we wanted to relate stress to displacement. So we can do that. So stress to displacement. Alright, so let's solve for the force in terms of stress. So the stress P equals L. Alright. Sorry, we're supposed to solve for P. Let's erase that. Let's write things a little smaller because we're gonna be running out of space real soon. So we can write that the stress maximum equals the modulus, or the base modulus, divided by the length equals the pressure. And therefore we can write the displacement equals the stress maximum Z L. Let's write this in, and then we can write P is taken up, right? So L over 3 divided by 3 E I. So we're continuing here. These two terms, they can be simplified. That sort of make it go away. Let's bring it back. Okay, they can be simplified. So what's Z divided by I? So basically B H squared divided by 6. I'm not giving any guarantees that this analysis is going to be correct, but I'm saying that perhaps this is one way to solve it. So BH3, so this cancels out completely, this out completely, this goes to 2, this goes to H. So it equals 2 over H. That's not hard. So basically the relationship between the displacement and the maximum stress, oh yeah, these two cancel, this becomes 2 then, is 3 E L 2H L squared. Hopefully I did all this right. So this is the wonderful formula we'll use for the stress. And again, okay, let's just keep using elastic modulus instead of elastic compliance. I explained the difference so many times. So we're taking the stress, and then we're going to try to get to strain. So what's stress and strain relationship? We saw before here. Stress times the modulus equals strain, or we can just write stress divided by the elastic modulus equals the strain. So we want to get that strain. So we divide. So basically, we have to the multiplication of these two equals the stress. So okay. Delta this equals strain times E. But this E in top and bottom are going to cancel, so I'm not even going to have that here actually. I'm not even gonna write that. So look at that. The deflection, the relationship between deflection and strain does not depend on the modulus, which makes pretty good sense. It doesn't depend on the base either, because that pressure, these two things are directly related. So I hope this is correct. Anyways, somebody else can double check it if they're really interested in finding this relationship. Maybe let me just check it online real fast. Well, I couldn't find it that easily, so we'll just continue. Again, we'll just repeat that result. The relationship between deflection and strain is going to be related to 2 over 3H L squared. And the units match too, because the units have to be in meters, and obviously strain is not in meters. So this is the maximum strain which exists. the average strain is what's going to be important for our piezo. Piezo is a linear material, so you can sort of use average is a really good way. So what do you take the average of anything? You divide it by 2. And dividing by 2 sort of cancels this 2 term out. So I am claiming, according to my result, which I don't know if it's correct or not, but it seems pretty good. This is a H. This is the relationship between the strain, not maximum, but okay, so the average strain, sorry, 2 times x average equals x what? Equals x maximum. So if you want to put this in here, we wouldn't actually cancel anything out. See all these mistakes that could go wrong. I don't know, I should have checked this a little better, but okay, let's see. 2, then make that 4, right? So let's just do 4x average divided by 3 and L squared over H. We'll just lump those two together. This will equal what? This will equal the displacement. So the next thing we want to do is determine what is the voltage of the piezo in this case. So if you want to apply a force to an open circuit piezo, it's going to be according to the strain is going to be according to the elastic compliance under constant electric displacement. So if we want to draw the stress, it's going to be like that. And the electric field generated is going to equal G times the stress. Substituting this equation and this one together, you solve for stress and you substitute. What we're going to get is this relationship between strain times G over SD equals G over SD is going to equal the electric field. And electric field times thickness equals voltage. So this equals voltage divided by thickness, right? So thus, if you want to write it more clearly in this box here, and in a different color, so it pops out, G over SD times the thickness times the strain average equals the voltage. So this is that. So, and what's E average here? E average can be calculated using this equation here. In this case, I solve for that, but if we rearrange the equation in terms of x average, we would have that displacement 3 over 4 h over L squared. This would be the average. Maybe I did something wrong. I would double check these equations, but I think the approach seems right. So we have some questions here. G is usually provided. Let's see if the other parameter. This is SD. The elastic compliance under constant electric displacement. If you have a parameter known as, so how do you calculate? So let's say you were given SE. How do you calculate SD? And we were talking about the 1-1 case. All these are 1-1 parameters. The G is G31 for the piezo. So we learned how to calculate now the average strain, the average maximum strain now. So if we had our cantilever, and we had at any point we have some type of stress distribution, maybe this is tension, this is compression here. We calculated now the average of this, and we know that if you're drawing, let's say, the tension on the top, you put a force here, the tension on the top is going to look like this. is going to decrease in, we'll call this level of stress, it's going to decrease linearly. It's going to be the highest here, and it's going to be the lowest at the tip. It's going to be actually 0 at the tip. So the tension force is going to be linearly decreasing. It's going to be maximum here. But in this case, for that equation that I used earlier, it calculates the stress maximum from which you calculate the strain maximum, and I took that average value, which then we can use for our piezo, because the strain is continuous between the host structure and the piezoelectric. So, long story short, in order, how do you calculate this to that? They're related, in fact. So, if you have the D31 coefficient squared divided by the permittivity, which is the 3,3, the normal permittivity you get, multiplied by the SE, this is known as a value called K squared. And SE, the elastic compliance under short circuit conditions, 1 minus K squared, is equal to the elastic compliance under electric displacement. And remember, usually when we're talking about Young's modulus is 1 over S. So I use here, for piezos, we usually use S. So we have, we used to have back here, we had elastic modulus as E. That's like the inverse. This is like stiffness. And compliance is like softness, you could say. So it's 1 over that. That's something not to get confused about. So we use this equation here. So let's keep going and let's just finish it up. If I can remember all of these parameters, that'd be great. So let's just note down the important equations. Delta 3/4 H over L squared. That's X. Oops, okay. That's X average. And the relationship between strain, G, SD times T thickness equals the voltage. So plug this in there. So the deflection, 3 divided by 4 H over L squared G over SD. Thickness. This is the thickness of the piezo. This is the thickness of the host. So that's still there. It doesn't cancel or it doesn't come together. This is the thickness of the piezo. That equals the voltage developed over the piezo in this case, where we have a whole structure, big whole structure. And we have a little tiny piezo top at the top, and this tiny piezo has a thickness TP, and this whole structure has a thickness H. So this will be the voltage developed, actually, in the open circuit condition, using the concept of average strain, the idea that the strain increases and decreases linearly. We're talking about displacement here. Although this whole thing displaces downward, there is stretching going on in this X direction here, and that is this displacement which causes strain. And there's actually strain at the top due to stress, and this strain here is what is going to be causing that voltage being developed. So these equations, you should double check them, but this is a general idea here. That we have our strain, we have our displacement, 3/4 multiplied by the height of the beam divided by the length of the beam squared times the G31 coefficient of the piezo. G31 is D31 divided by epsilon 33 capital X, free stress, divided by SD, which then we defined earlier using K squared, and TP, which is thickness of the piezo. If you increase the thickness of the piezo, you're going to get more voltage, but you're also going to get a thickness sort of scaling. So that's something to note. The piezo become more stiff. You won't get as much displacement because you're increasing this H. You're increasing whatever. So thanks for watching. Oh, it'll be harder to deflect. You'll need more force to deflect. Right now we're using the relationship between deflection and strain. However, you'll get less deflection if your piezo is thicker. So just different things to note, and if you want to optimize or whatever. But this works pretty well. I hope this equation is correct. Somebody may look it up, or you may not, but here it is. Thanks for watching. In the next video, I might try to verify this. The purpose of these videos is to show how one might go about analyzing piezos, and I'm not going to hold myself liable for any mistakes in this analysis. Sorry. This is not something I took out of a textbook. It's something I sort of just concocted right now. So with that, I'll see you in the next video for some FEA analysis to try to verify this equation. Maybe I missed like a 3/4 over here somewhere. Let's take a look at it. See you in the next video.